In this video, we are going to talk about solutions of second-order linear homogeneous equations and also the Wronskian. In our previous video, we solved some simple second-order linear homogeneous equations with constant coefficients. And before we go on to learn how to solve other second-order linear equations, we're going to review what we can expect out of solutions. There are quite a few theorems in this video. So much so that my overview slide, which is usually one slide, has become two slides. But many of them have analogs when we looked at first-order linear equations, so they will seem somewhat familiar. Of course, it's important you keep in mind, now we're talking about second-order linear equations. And I just will remind you that a second-order differential equation is one that relates a second derivative to an independent variable t, the function y itself, and its first derivative. We will start by talking about a differential operator, and we'll denote that differential operator by the letter L. And essentially what that is, it's a function, and for inputs, it takes other functions, and then it outputs another function. So for example, if L phi of t, where phi is a function of time, is equal to phi double prime of t plus t squared phi prime of t plus 1 plus t phi of t, then L sine of 3t, so we plug in a function 3t into this other function L, or operator L, and we get phi double prime, so that'll be sine 3t double prime, plus t squared, this is our function p, times phi prime, sine of 3t prime, plus, and then q in this instance is 1 plus t times sine of t. And then, of course, you would take the second derivative and the first derivative here and multiply everything out. And we're going to use this notation and idea of a differential operator now when we talk about solutions to our second-order linear homogeneous equation. So in particular, in this section, we're going to study second-order linear homogeneous differential equations, and we use this L, L operator, which we'll usually write in the form L of y is equal to y double prime plus p of t y prime plus phi of q of t y equals 0. So it's the same equation here, but instead of the phis, we have y's. And we have an initial condition, y of t naught is equal to y naught, and y prime of t naught is equal to y prime naught. We'll look at a theorem of existence and uniqueness, which actually should look very familiar because it looks just like the one for first-order linear equations. So if we consider the initial value problem, y double prime, so it's second order, plus p of t y prime plus q of t y equals g of t, where we have initial conditions, and p, q, and g are continuous on an open interval I that contains the point t naught, then this problem has exactly one solution, so a unique solution, and the solution exists throughout the interval I, so very much like first-order linear equations. Then we have the general solution. So first is the principle of superposition, which you've been using since the last chapter. So if y1 and y2 are two solutions of the differential equation, then the linear combination is also a solution. In other words, c as a constant times y1 plus another constant times y2 is also a solution. We've been using that to create a general solution. But as we saw even with first order differential equations, that this linear combination, if the first order equation is not linear, if it's nonlinear, then it's possible that there are solutions that do not have this form. However, if it's linear, then this form will cover all solutions. It's the same here for second order. So general solutions, suppose that y1 and y2 are two solutions of the second order differential equation, then the two parameter family of solutions, y is equal to c1 y1 plus c2 y2 with arbitrary coefficients c1 and c2 includes every solution of the equation. And here we have an if and only if there's a point t naught where the Wronskian of y1 and y2 is not 0. So we haven't defined the Wronskian, but it's here and we will do some examples of that. But that is the same idea that in general, often this will cover this form. Once you have two solutions, when you take a linear combination, that'll cover all the solutions. So there are no solutions that don't have this form, except we have this condition, if and only if the Wronskian is not zero. And then we have two more theorems. The first one is the complex value solution, and this theorem we're actually not going to use really until the next chapter or next video. But so I'm not even going to read it, but it's here. And then the next theorem is Abel's theorem, which gives you a way of calculating the Wronskian without actually solving the differential equation. So again, we'll go through this with examples. Okay, as I said, we would start with the differential operator notation. So let P and Q be continuous functions on an open interval I, that is, T is between A and B, that's our interval, where A can be negative infinity and B can be infinity. Then for any function phi that is twice differentiable on I, we define the linear operator L by the equation L of phi is equal to phi double prime plus P, a function of T, phi prime plus Q, another function of T, times phi. So again, the results of applying the operator L to a function is another function. So you plug in a function phi and you get a different function out. And we refer to this as L of phi. The value of L of phi at a point T is denoted with L of phi of T, and that's just phi double prime of T plus P of T, phi prime of T plus Q of T, phi of T. And our example again, if L of phi of T is equal to phi double prime of T plus T squared phi prime of T plus 1 plus T phi of T, in this case, right, our P of T is T squared, and our Q of T is 1 plus T. So here we have an operator that takes a function and it produces another function. So for example, if we plug in sine of 3t to this function, we get sine of 3t double prime plus t squared sine of 3t prime plus 1 plus t sine of 3t. Then taking the second derivative, we'll get negative 9 sine of 3t. The first derivative, we get 3t squared cosine 3t, and then here we get 1 plus t sine of 3t. This isn't really something super complicated, but it's just a notation we use, and you kind of think of this as an operator or a function that takes a function and produces another function. A couple of notes: the operator L is often written as this D, a capital D. So L is equal to D squared plus PD plus Q, where D is the derivative operator. So second derivative plus P times the first derivative plus Q. And we usually write this in this form, L of Y. So instead of the phi, we often put in Y. So we have Y prime plus P of T Y prime plus Q of T Y equals 0. So this should be a familiar form for our differential equation. And then we can also have our initial conditions. So in this section, we studied the second order linear homogeneous differential equation, where we set this equal to 0. That is, here. And we'd like to know where the initial value problem always has a solution and whether it may have more than one solution. We'd also like to know whether anything could be said about the form and structure solutions that might be helpful in finding solutions to a particular problem. And our first answer to this about whether or not we have solutions is the theorem of existence and uniqueness. So consider the initial value problem y double prime plus p of t y prime plus q of t y equals g of t, with the initial values y of t naught equals y naught and y prime of t naught equals y naught prime, where p, g, and q are continuous on an open interval I that contains the point t naught. So this problem has exactly one solution, y equals phi of t, and the solution exists throughout the interval. So this theorem is totally analogous to existence and uniqueness for first order linear equations, and this is the second order linear equations. Again, wherever p, q, and g are continuous, that's where you'll have a solution for the initial value problem. And just some other notes, exactly what the existence and uniqueness theorem says. The initial value problem has a solution, that is, a solution exists. The initial problem has a unique solution. And last, the solution is defined throughout the interval by where the coefficients are continuous, the coefficients being p, q, and g. And so where the coefficients are continuous and at least twice differentiable. The last important note is for most problems of the form y double prime plus pt y prime plus qty equals gt, the general second order differential equation, linear differential equation, it is not possible to write down a useful expression for this solution. This is a major difference between the first order and second order linear differential equations. Therefore, all parts of the theorem must be proved by general methods that do not involve having an expression for the solution. And this proof of the existence and uniqueness of solution is fairly difficult, and we do not discuss it here. So we will use this theorem, existence and uniqueness, to find the longest interval in which the solution of the initial value problem below is certain to exist. So we have t squared minus 3t times y double prime plus ty prime minus t plus 3y equals 0, and y1 equals 2, y1 prime equals 1. According to our theorem, to find out where the solution exists, we need to look at p, q, and g to find where they are continuous. So p, q, and g. So here is our y double prime. First, we need to put it in the correct form so that y double prime doesn't have anything in front. So here I divide everything by t squared minus 3t to put it in this form that I want here. And I get y double prime plus t over t times t minus 3y prime minus t plus 3 times t minus 3y equals 0. And then I canceled out these t's here, so I come up with y double prime plus 1 over t minus 3y prime minus t plus 3 over t times t minus 3y equals 0. I thought these might simplify, but they don't. And as I was saying, according to our theorem, to find where the solutions of this differential equation exist, we have to look at p, q, and g. So in this case, p is equal to 1 over t minus 3, and q is equal to t plus 3 over t times t minus 3, and g is equal to 0. We just need to find where these are continuous. And as you can see, p of t is continuous everywhere except t equals 3, so continuous as long as t does not equal to 3, and q of t is continuous as long as t doesn't equal 0, and t does not equal to 3. So our intervals are negative infinity to 0, 0 to 3, then 3 to infinity. So the longest interval containing the initial value point, t naught equals, where do I have my initial value? Here. T naught equals 1 is 0, 3. So, which is where the solution is guaranteed to exist. Actually, this should be t naught is equal to 2, but that's still in the same interval, 0 to 3. Our next example is to find the unique solution of the initial value problem where p and q are continuous on an open interval I containing t naught, and we have the general equation y double prime plus p of t y prime plus q of t y equals 0, y of t naught equals 0, and y prime of t naught equals 0. Now this seems like we would have to start doing something complicated, except that our theorem of existence and uniqueness, in particular the uniqueness, gives us a way to easily solve this problem because there's one obvious solution to this equation. And that would be the trivial solution where y of t is equal to 0, since y double prime would be 0, y prime would be 0, and y would be 0, so this whole equation is 0. And so this is one solution, but since we have this theorem of uniqueness, it is the only solution. And by the way, when I talk about the trivial solution, I specifically mean 0. 0 is the trivial solution. I don't mean that it's unimportant. now that we have talked about the theorem of existence and uniqueness, we can go on and talk about principle of superposition and the general solution. So the principle of superposition is one that we've been using since the last chapter, since the beginning of the book. So if y1 and y2 are solutions, or two different solutions of the differential equation, L of y is equal to y prime plus p of t y prime plus q of t y equals 0, then the linear combination, in other words, a constant times y1 plus another constant times y2, is also a solution. And the proof of this theorem is fairly straightforward. We start by letting y1 and y2 be solutions of our y double prime plus p of ty plus q of ty equals 0. So in other words, L of y1 is equal to y1 double prime plus p of y1 prime plus q of y1 equals 0. And same for L of y2. It basically solves this equation, or fits this equation. So now we need to look at the linear combination c1y1 plus c2y2, plug it into L. So plugging this in, we get c1y1 plus c2y2 double prime plus p times y prime, which is c1y1 plus c2y2 prime, plus q times y, c1y1 plus c2y2. And we want to show that that equals 0. Because of properties of derivatives, the c1y1 plus c2y2 double prime, we can separate this out, and this is just a constant, so we pull the constant out and we get c1y1 double prime plus c2y2 double prime. Similarly, over here, this is just p times c1y1 prime plus p times c2y2 prime plus q c1y1 plus q c2y2. And again, the way I distribute this prime to the y1 and y2 is just because the derivative is a linear operator. In other words, if I have a function f plus a function g and I want to take its derivative, that's just equal to f prime plus g prime. And if I have constant coefficients in front, they just get added in front too. So that's exactly what we're doing here. We have a second derivative, or a first derivative, of two functions, y1 and y2. So we can just take the second derivative of y1 and add the second derivative of y2. Similarly here with the first derivative, and the constants just get added in front. And now what I can do is rearrange the terms, or group the terms. So I put all my y1 terms over here and my y2 terms over here. And now I can pull out my constants. So I pull out c1 and c2, and what I get now is c1 times L of y1 plus c2 L of y2. But now L of y1 and L of y2 are both equal to 0. So I have c1 times 0 plus c2 times 0, and that's equal to 0. And therefore, our c1y1 plus c2y2 is a solution to this linear equation produced by the linear operator. So back to the principle of superposition. So we proved that it was true that once you had two solutions to this linear operator, then the linear combination of your two solutions is also a solution. So here, the first point is, beginning with only two solutions, y1 and y2, we can construct an infinite family of solutions. And we say infinite family because there's an infinite number of ways of choosing c1 and an infinite number of ways of choosing c2. And it's a family because there's an infinite choice for c1 and another infinite family for c2. And are all the solutions of the equation included in y equals c1 y1 plus c2 y2? In other words, are there solutions that have a different form? To answer this question, we will begin by examining whether the constants c1 and c2 can be chosen so as to satisfy these initial conditions. Y of t naught equals y naught, and y prime of t naught equals y naught prime. So essentially, we have these two equations that must be satisfied. So we need to choose c1 and c2 so that they're both satisfied, that c1 y naught t naught plus c2 y naught t naught is equal to y0. That's to satisfy this first initial condition. For the second initial condition, we need c1 y prime of t naught plus c2 y prime of t naught to equal to y naught prime. And taking a little trick from linear algebra, this system of equations can be represented by this matrix multiplication or this matrix equation. So I take my C1 and C2 over here as a vector, and then I take these other coefficients, the things that multiply C1 and C2. So I have my y naught of T naught, my y2 of T naught, my y1 prime of T naught, and my y2 prime of T naught times C1, C2. And if you remember how to multiply a matrix times a vector, it's essentially this row dot this vector is equal to this first element of this vector. The second element is equal to the second row dot this vector. So looking at this y naught here, again, it's the first row dot this column. So y1 T naught times C1 plus y2 T naught times C2. So that's this equation here. Then the second equation comes from y1 prime T naught times C1 plus y2 prime T naught times C2 is equal to y naught prime. So again, that's the second part of our matrix multiplication. It's this row dotted with this column gives us this one. And you can see that multiplying this matrix out gives you this system of linear equations. And if you've had linear algebra, you know that this matrix equation has solution if the determinant of this matrix here is not equal to 0. If you haven't had linear algebra, there isn't a whole lot here you really have to know, except that you're going to look for the determinant of this matrix here. y1 T naught, y2 T naught, y1 prime T naught, y2 prime T naught. And hopefully you remember how to find a determinant, but if you don't, that's okay, because we're only doing 2 by 2. It's this cross multiplied, so you have the y1 T naught times y2 prime T naught minus this cross multiplied. So then you have your minus, which is important, y1 prime T naught, y2 T naught. And what we will find, so if now the determinant of this matrix is not equal to 0, the equations have unique solutions, C1, C2, regardless of the value of y naught and y naught prime. In other words, there's always a solution to whatever initial value problem you have. And then there's this formula for you to calculate C1 and a formula to calculate C2. But one thing to remember is this bottom part here is this W, the Wronskian, the determinant of the matrix that represents the coefficients of this matrix equation, or the system of equations. And one other note that I needed to squeeze in on this page is here. If W is equal to 0, there are no solutions unless the numerator is equal to 0. So if W equals 0, there are many initial conditions that cannot be met. And here I kind of summarized what we had. We had our system of linear equations that needed to be satisfied to satisfy these initial conditions, and we transformed that into the coefficients, the matrix of coefficients, times the coefficients C1 and C2 that we're trying to solve for, given this solution of y naught and y naught prime. And from linear algebra, we know that this has solution for any y naught prime when this matrix here, the determinant does not equal to 0. The determinant of this matrix we call the Wronskian, denoted with this capital W, and it's equal to, the determinant is just the cross multiplication of these two minus the cross multiplication of these two. So again, it's the Wronskian determinant, also denoted with a W, or sometimes a W of y1, y2 of T naught. And again, if W does not equal to 0, the equations have unique solutions C1, C2 for any value y naught and y naught prime. And here is our theorem. Suppose that y1 and y2 are two solutions to the differential equation y prime plus pty y double prime plus pty plus q of ty equals 0 with these initial conditions, then it is always possible to choose constant c1 and c2 such that y equals c1 y of t plus c2 y2 of t satisfies the differential equation at initial conditions if and only if the Wronskian is not equal to 0. So I moved the theorem up here as well as the formula for the Wronskian so we can do some examples. The first one is to find the Wronskian of y double prime plus 5y prime plus 6y equals 6. So I couldn't resist solving this equation because that seems like what we should be doing, but we will also calculate the Wronskian once we solve this. So if we recall, this is a second order linear differential equation. It's homogeneous because it's equal to 0. Also, it has constant coefficients. So we learned how to solve this in the previous video. And what we saw is when we have this y double prime equals y type of thing, that we guess that the solution is going to involve e to the rt. So we assume that y equals e to the rt, y prime then would be r e to the rt, and y double prime is equal to r squared e to the rt. Substituting in y over here, y prime here, and y double prime here in this equation, we get r squared e to the rt plus 5 r e to the rt plus 6 e to the rt. Factoring out the e to the rt, then we get r squared plus 5r plus 6, which then factors to r plus 3, r plus 2 equals 0. And remember, this is what we call the characteristic equation, and when we solve it, we find r1 is equal to minus 3 and r2 is equal to minus 2, which means y1 is equal to e to the minus 3t and y2 is equal to e to the minus 2t. So our general solution is a linear combination of y1 and y2, which is c1 e to the minus 3t plus c2 e to the minus 2t. Now we're ready to solve for the Wronskian. Actually, yeah, we did need to solve it because we need y1 and y2. So we need y1 t naught. So that will be e to the minus 3 t naught. y2 t naught will be e to the minus 2 t naught. Then y prime of t naught will be minus 3e to the minus t, and y 2 prime at t naught is minus 2e to the minus 2t. Now cross multiplying here, I get minus 2, and these multiplied together gives us e to the minus 5t. Cross multiplying here, but I need to subtract it, so I get a plus because of this minus, will give me a 3, and then again e to the minus 5t, which equals e to the, adding these together, I get e to the minus 5t, which is never equal to 0. So since w is not equal to 0 for any value of t, then y equals c1 e to the minus 3t plus c2 e to the minus 2t is the solution for the initial value problem prescribed at any t. In the interest of time, I decided not to cover this proof, but I have it here for your reference. There's one more thing to show in this proof. Here is the rest of the proof, and what we want to note that if the Wronskian is equal to 0, there may be solutions, but they are not going to be of the form y equals c1 y1 plus c2 y2. And here is that last point. So if the Wronskian is equal to 0, there may be solutions that are not of the form of the linear combination of y1, y2. And remember, y1, the Wronskian is with respect to the particular y1 and y2 you choose. Now, if there is a point where the Wronskian is not 0, then this linear combination does encapsulate all of the solutions, and it is called the general solution. And also y1 and y2 are called the fundamental set of solutions. Here is our first example to demonstrate the Wronskian and the fact that if it's equal to 0, there may be solutions outside the linear combination. If it's not 0, then the linear combination is the general solution, and y1 and y2 are called the fundamental set of solutions. So suppose that y1 is equal to e to the r1t, and y2 is equal to e to the r2t, and they're solutions of this differential equation, y double prime plus py prime plus qy equals 0. Show that if r1 does not equal to r2, then y1 and y2 form a fundamental set of solutions. Looking at this statement here, it's a fundamental set of solutions if the linear combination c1y1 plus c2y2 is the general solution, which happens, according to our theorem, if and only if w is not equal to 0. So I've written that here. Fundamental set of solutions if the linear combination is a general solution, which is if and only if w does not equal 0 for some t naught. Here I calculate w. Again, it's y1 and y2 here, with the derivative of y1 and the derivative of y2 here. And then the determinant I cross multiply, and I get r2 e to the r1 plus r2t, minus, and I cross multiply here and get minus r1 e to the r plus r2t, which is r2 minus r1 e to the r1 plus r2t. And looking at this, if r1 does not equal to r2, then the Wronskian will not equal to 0. So y1 and y2 form a fundamental set of solutions. Here is our next example. Show that y1 equals t to the 1/2 and y2 equals t to the minus 1 form a fundamental set of solutions for 2t squared y prime plus 3t y prime minus y equals 0, where t is greater than 0. The first thing I need to do is to show that y1 and y2 satisfy this differential equation. In other words, they are solutions to the differential equation. And I know it's easy to forget this step because you kind of are led down the garden path because they're called y1 and y2. You kind of automatically assume they're solutions, but really you should verify that. So here I have y1 is equal to t to the 1/2, which means y1 prime is equal to 1/2 t to the minus 1/2, and y double prime is equal to the minus 1/4 t to the minus 3/2. I plug in y prime, and y double prime into this equation here, so I get 2t squared y double prime plus 3t y prime minus y, and I see through some algebra I get that equals 0, which is exactly what this solution is. I do the similar thing for y2 to verify that y2 also solves this differential equation. I can always take linear combinations of y1 and y2, and they will also be solutions to this differential equation. We saw that by the theorem of superposition. However, what we don't know is if all solutions are of the form c a constant times y1 plus a different constant times y2. But that's exactly what the Wronskian will tell us, is whether or not it is the general solution. So here I have y1 and y2, and then I have the first derivative of y1 and the first derivative of y2. I take the determinant, and I get minus 3/2 t to the minus 3/2. So you can see that this is not equal to 0, and except at t equals 0, or w, the Wronskian is equal to 0 only when t is equal to 0. But our problem statement says that t is greater than 0, so that's not a problem, which means that our linear combination c1 t to the 1/2 minus c2 t to the minus 1 is the general solution, and then y1 equals t to the 1/2 and y2 is equal to minus t to the minus 1 is the fundamental set of solutions. And I'm going to change this here to say a fundamental set of solutions because there are more than one possible sets of fundamental solutions, and we'll talk about that more in a minute. And then I have my Wronskian theorem here, as well as kind of the two comments about if the Wronskian is equal to 0, there might be solutions outside the linear combination. If it's not 0, then the linear combination is the general solution. And the question is, does a differential equation of the form y double prime plus pt y prime plus qt y equals 0 always have a fundamental set of solutions? It kind of seems like no, because if w equals 0, well, anyway. So it's difficult to find a fundamental set. If it's difficult to find a fundamental set, we might want to know if they even exist. And here's the theorem, and you will see exactly in the proof that it does depend on the Wronskian, but it's a little different from our other theorems, so I'll show them side by side in a minute. But let's just look. The existence of the fundamental set of solutions. Consider the differential equation, the second order, y double prime plus pt y prime plus qt y equals 0, whose coefficients p, q are continuous on some open interval that we call I. Choosing some point t naught in I, let y1 be the solution of the differential equation that also satisfies the initial conditions. Yt of naught equals 1, yt naught equals 0, y prime t naught equals 0. And let y2 be the solution of the equation that satisfies the initial condition yt naught equals 0 and y prime of t naught equals 1. So here y1 and y2 satisfy these particular initial conditions. So this is what makes it a little different from the other theorems. But the idea is then y1 and y2 form a fundamental set of solutions to the differential equation. And we'll see the proof depends on the Wronskian because that's exactly what this is talking about. The Wronskian is talking about when you have general solutions and therefore fundamental solutions. So the existence is guaranteed by the theorem of existence and uniqueness. So I said it's good to kind of compare these two because they look so similar. So here we're looking at the initial value problem. So again, we have the same form, y double prime plus pt, y prime plus qt, y equals g of t. Of course, this now we have 0. It's the homogeneous equation. This is not. And then we have, and here we have general initial conditions. Here we have specific. But it says if p, q, and g are continuous on the interval that contains the point t naught, then there's exactly one solution. So this is a subset of this theorem, right? Because basically here g is equal to 0 and 0 is continuous. And so this is like arbitrary initial conditions. Here are particular ones. But this theorem, the existence and uniqueness, will certainly apply here. So there is a solution. And then to show they form a fundamental set, I need to show the Wronskian is not equal to 0. Again, this all depends on this Wronskian. So w, y1, y2, here I have y1 and y2 both evaluated at t naught, and then I have y1 prime and y2 prime evaluated at t naught. But these are given to me here in the conditions of my theorem. So I have y1 at t naught is 1, y2 at t naught is 0, and then y1 at t naught is 0, and y2 prime at t naught is 1, right, given by my initial conditions. And so cross-multiplying, I get 1 is the answer, which is not equal to 0, so they do form, so the linear combination is a general solution, and y1 and y2 do form a fundamental set of solutions. Here's a question. Find the fundamental set of solutions for the differential equation y double prime minus y equals 0 using t naught equals 0. We had solved this equation before in like 3.1, video about 3.1, where we have y double prime is equal to y. And there are two solutions to that. So y1 is equal to e to the t, and you can verify when you take the second derivative, you'll get e to the t. And y2 is equal to e to the negative t. Right, so the derivative will give you negative e to the minus t. The second derivative will bring you back to e to the minus t. One thing to notice though, if we want to use this theorem here to show that these two equations, y1 and y2, are a fundamental set of solutions, then our y1 and y2 has to satisfy these initial conditions. First, that this is if y1 is a solution, it satisfies y1 t naught is equal to 1, which looks like that looks just fine. T naught is equal to 0, so y of 0 is equal to, if we plug in 0 here, we get 1. So that's satisfied. But now if we look at y2 of 0, here, let y2 be the solution of satisfying these initial conditions, so y of t naught has to equal to 0. But in this case, using t naught equals to 0, when we plug that into y2, we get 1. So these two equations, because of y2, will not satisfy the initial conditions, and they are not the set of fundamental solutions that are guaranteed by this theorem. I just kind of summarized what I just said in a note. So because y2 at t naught does not equal to 0, which is part of the conditions of this theorem, we cannot apply the existence of fundamental set of solutions theorem to y1 and y2, and say that y1 and y2 are a fundamental set of solutions. However, I can use this theorem here about the Wronskian to show that y1 and y2 are fundamental solutions. I can calculate the Wronskian. Here's y1, y2, derivative of y1, derivative of y2. You see the Wronskian's -2, which is never equal to 0, which means these two equations, remember, are then fundamental solutions. So keeping those two things in mind, we're going to square them right now. So the interesting thing is y1 equals e to the t and y2 equals e to the minus t are fundamental solutions by the Wronskian theorem. And y equals c1 e to the t plus c2 e to the minus t is the general solution. And again, y1 equals e to the t and y2 equals e to the negative t do form a fundamental set of solutions. But this is where it gets interesting. Because y1 and y2 do not satisfy the initial conditions of this theorem, the existence of fundamental set of solutions theorem, they are not the fundamental set of solutions guaranteed by the theorem. In other words, there's another fundamental set guaranteed by this theorem that is not equal to this e to the t or e to the minus t. So we can start the hunt for this extra set of fundamental set of solutions. We'll start with y3, and the thing we know about y3 is that it has to be of the form c1 e to the t plus c2 e to the minus t, because the Wronskian told us that this is the general solution. So we have y3 as our linear combination of e to the t and e to the minus t. But this solution here is the one that satisfies the fundamental set of solutions, and that tells us if y1 is the first solution, then it has to satisfy the initial conditions that y t naught equals 1 and y prime t naught equals 0. So I have that here. Y t naught, remember t naught is 0, is equal to 1, and y prime of t naught is equal to 0. Plugging this in, so y of 0 is equal to 0. No, this should equal to 1, which is equal to c1 plus c2. I can easily find a c1, c2 that equals 1. In fact, y3 is equal to 1/2 e to the t plus 1/2 e to the minus t will be my solution. And if you know your cosh, your trigonometry functions well, you will recognize this as cosh of t. And if you don't know, you can just take my word for it, but maybe jot this formula down somewhere. We can do the same with y4. Now again, we know it's a linear combination because this is the general solution of e to the t and e to the minus t. So I've written that down here, and it satisfies. So now we're looking at the second solution. It has to satisfy y of t naught equals 0 and y prime of t naught is equal to 1. So y of t naught equals 0, y prime of t naught is equal to 1. So I plug that in, and I get 0 is equal to c1 and c2. So I can plug in y4 is equal to 1/2 e to the t minus 1/2 e to the minus t, which is equal to sinh of t. And just to summarize everything, this is the same problem we were working on. We have y3 is cosh of t, y4 is sinh of t. I can calculate the Wronskian, and I'll see it's equal to 1. That means that this is the general solution, c1 times cosh of t plus c2 sinh of t, and y3, which is cosh of t, and y4, which is sinh of t, are a fundamental solution set. So now we have two fundamental solution sets, the easy one and the other one that took a little more work to get to. And honestly, if you have this fundamental solution set, I wouldn't go searching for a second one. But the point of this example is that there was another one that fit this theorem here. And for a given differential equation, there are actually infinitely many fundamental sets of solution. And as a rule, you should choose the set that is most convenient for your purposes, which is why I would have stopped right here. But this is something that you need to remember. As a rule, and we're going to see other examples of that, especially in the next video, as a rule, you can choose the set that is most convenient. Now we've covered our theorem of existence uniqueness, our principle of superposition that says the linear combination of two solutions is also a solution. We talked about the general solution and how the Wronskian will let us know if there's a general solution and fundamental solutions. There was this other theorem about existence of fundamental set of solutions, but you have to have your y1 and y2 specifically satisfy these initial conditions, but it does guarantee a particular fundamental set of solutions. Now we were ready to talk about the complex valued solutions theorem, which honestly, we're not really going to use it in this chapter. It's more applied in the next chapter, but it might be in your homework, so we'll go through it. And then we'll also talk about Abel's theorem, which is a really convenient way of calculating the Wronskian without actually finding these y1 and y2 solutions. Here's my next theorem that I said I wasn't going to even read, but I'm going to. And actually this theorem, we are going to use it in the next video. But complex valued solutions. So let's say we have a second order linear differential equation that y double prime plus pt y prime plus qt y equals 0, where p and q are continuous, real valued functions. And by real valued is when you evaluate t at p, you're going to get a real number. That's what it means to be real valued. When you evaluate q, you're going to get a real number. They don't produce, p and q do not produce complex numbers. So if y is equal to u of t plus I v of t is a complex valued solution of the differential equation, we're going to get those in the next video. So if it happens that a solution to this equation has a real part and a complex part, this I v of t is our our imaginary part, then its real part u and its imaginary part v of t, which is, this v of t is real, but it becomes the imaginary part because it's multiplied by I. So this u of t and this v of t are also solutions to this equation. And another side note, the complex conjugate, u of t minus I v of t, is also a solution. Given that I barely even wanted to read this theorem, I'm just going to leave this proof here for your reference. Our last theorem is Abel's theorem. If y1 and y2 are solutions of the second order linear differential equation, y double prime plus pt y prime plus qt y equals 0, where p and q are continuous on an open interval I, then the Wronskian is given by, so here we have another formula for the Wronskian, and you notice it doesn't involve finding y1 and y2. And I'm not going to go through the proof of Abel's theorem, but I do have it outlined here. It's actually pretty short. One note here, so the Wronskian, if you have two fundamental sets of solutions, like that last problem where we had two fundamental sets of solutions for y double prime is equal to y, then the Wronskian, so two fundamental sets of solutions of the same differential equation can differ only by a multiplicative constant. In other words, for those two fundamental sets of solutions, if you calculate the Wronskian of the first set and the Wronskian of the second set, they will be they'll be the same except for a multiplicative constant. And also, since the Wronskian is either always 0 or never 0, you can determine, that's from this proof here that we get this, the Wronskian is either always 0 or never 0, you can determine which case actually occurs by evaluating w at any single convenient value of t. So this is kind of useful here, and it falls out of this proof. So I have Abel's theorem here and the 2 points about the Wronskian here, and we'll look at an example. So in a previous example, we verified that y1 equals t to the 1/2 and y2 is equal to t to the minus 1 are solutions to the equation 2t squared y double prime plus 3t y prime minus y equals 0 for t greater than 0. We're going to verify the Wronskian is given by Abel's formula. And just to review, we had calculated the Wronskian earlier, but I repeated the calculation here. Here's y1, y2, y1 prime, y2 prime, and it's equal to minus 3/2 t raised to the minus 3/2. From Abel's theorem, we can calculate that the Wronskian is equal to c times the exponent of negative p of t dt. So looking at this here, well, I need to get this in the right form, so I have to divide everything by 2 over t squared, and I get y double prime plus 3/2 t to the minus 1 y prime minus y equals 0. So plugging in then, what does this look like? It looks like my p of t is equal to 3/2 t to the minus 1. So I'll plug that in, and then I'll have c exp to the minus integral of 3/2 t to the minus 1 dt. This here is equal to 3/2 natural log of t. So what I have is c e raised to the minus 3/2 natural log of t, which is equal to c, this becomes the exponent t to the minus 3/2, which is exactly what I got before. And for this example, this example here, our c was equal to minus 3/2. We're ready to review what we looked at. First, we looked at the differential operator, which we designated with L. And what that is it takes a function phi and it produces another function. And our example here, we had done it is if we take L is equal to phi double prime plus t squared phi prime of t plus 1 plus t phi of t, when we plug in our function sine of 3t, we get phi double prime, which is sine 3t double prime, t squared times phi prime, so t squared times sine of 3t prime, plus 1 plus t times phi of t, which is sine of 3t. And of course you would figure out what sine 3t double prime is and sine 3t prime is. We looked at the existence and uniqueness theorem for a second order linear equation, which is y double prime plus pty prime plus qty equals g of t. And it looked very similar to the existence and uniqueness theorem for first order linear equations, which is, we also have these initial values. Y t naught is equal to y naught, and y prime of t naught is equal to y naught prime. So this here, this additional prime, this additional initial value was not in our first order, but for second order we have this additional initial value. But essentially, this equation, this initial value problem, has solution where exactly where p, q, and g are continuous on an open interval I that contains the point t naught. So this problem has exactly one solution, y equals phi of t, and the solution exists through the same interval I that p, q, and g are continuous. We talked about the principle of superposition. That is, if you have two solutions to a differential equation, then any linear combination of those two equations is also a solution. They might even be the general solution, and if they're the general solution, what that means is every solution of this second order linear differential equation is of this form. So if every solution is of this form, then this form is the general solution. And then we said that we can determine if it's a general solution by looking at the Wronskian, and we verify that the Wronskian is not equal to 0. So if the Wronskian is equal to 0, that means there may be solutions that do not follow this form. If it's not 0 from some point t naught, then the linear combination is called a general solution, and y1 and y2 are called a fundamental set of solutions. And we talked about how to calculate the Wronskian with this determinant formula. I added this slide to my summary set, but I didn't add it with the next slide because it didn't really fit in there. So this really is part of bullet point number 3. So we did talk about the existence of a fundamental set of solutions. To use this theorem here to find out if y1 and y2 are a set of fundamental solutions, you can determine that but you can only use this theorem if y1 satisfy these initial conditions and y2 satisfy these initial conditions. But from this theorem, we did an example where we found a fundamental set of solutions, but it wasn't the fundamental set of solutions guaranteed by this problem. So then we found another set of fundamental solutions, and the moral was a given differential equation has infinitely many fundamental solutions, and as a rule, you should choose the set that is most convenient. And by most convenient, I mean the one that you happen to think of, or the one that has the simpler equation. And this will become more clear in the next chapter. Our last part of this summary is we talked about complex value solutions. So if you have a solution to a second order equation that has a complex value, and the complex value looks like a real number plus I times a real, I'm sorry, not a real number, but a real valued function plus I times a real valued function, then U of t and V of t are also solutions to this equation. Last, Abel's theorem allows us to calculate the Wronskian without finding the y1 and y2 solutions. So this was kind of a long video. The next one will be shorter, so hang in there. Thank you for watching.